We will have sufficient time. We will have sufficient time for discussion at the end with Dr. Praveen, faculty advisor of the student chapter, will be the moderator. Now, without any further ado, we will turn the time over to Mr. Mihir. Sir, over to you.
Thank you, Ipshita. So, hello everyone. I'll take it from here. My screen is visible, right?
Yes, Mr.
Okay, sir. Thank you. So, hello everyone, and welcome to today's hands-on training session, where we will be talking about nonlinear analysis and seismic analysis of RC frame building. This is Mihir Jain. So, before we start the session, like as Ipshita mentioned, you can post any questions in the tab as well, and we will discuss that at the end. So, feel free to write any questions or any doubt that you have throughout the session. So, first we will be covering like the goals. The goals for this session is to understand about different nonlinear analysis, because situation where the nonlinear analysis is required. So we'll be focusing what are the different approaches for that. Then we will focus majorly on seismic analysis. So as an earthquake resistant engineer and designer, we need to understand what are the different types of analysis that are present to perform seismic analysis. Then the major focus will be on the pushover analysis to find the capacity curve of the building. And we will also discuss its significance. And then as it is a hands-on training, so we will be performing the demonstration, where the demonstration will be done on ETABS. So as mentioned, like you can just on the ETABS model, like when we start the demonstration, and you can start the steps following with me. Coming to the contents. So the first, we will talk about introduction to nonlinearity. Then we will focus seismic analysis, pushover time history analysis. Then I'll give you the structure overview that we are modeling today. And then we will quickly move towards the ETABS demonstration. And at the end, we will conclude this session. So coming to the introduction. So if I talk about a nonlinear analysis, so a nonlinear analysis is an analysis where applied force and displacement holds a nonlinear relation. And if I put it into some other terms, then the stiffness of the structure is no longer constant, but varies with respect to the loading. So these are some major crux of the nonlinearity that I want to discuss. And if I talk about any nonlinear condition, so it can be of three types. The first is a geometric nonlinearity, then the second material, and the third contact nonlinearity. So if we further discuss about that, the geometric nonlinearity is majorly focused with the large deflection that is occurring in the structure, where buckling can be an example of that, of geometric nonlinearity. Then if we talk about material nonlinearity, so we know that beyond the elastic limit, the material don't follow the straight modulus of elasticity. Like the curve is not straight, the slope is changing at different point. So that is where the material nonlinearity comes. And also the creep is another example of the material nonlinearity option. Then if we talk about the contact analysis, so here the different frictional contacts that come into picture when we are dealing with any mechanical problem or any mechanics. So then also these are the contact nonlinearity that can occur. Discussing further on these topics. So the very first, geometric nonlinearity. So changing geometric configuration due to large deformation of the structure causes nonlinear behavior. And geometric nonlinearity is not only because of large deformation, but also due to large strain and large rotation too. As I mentioned, geometric buckling is an example of geometric nonlinearity. And here you can see, like for an example, we are having a trampoline, which is like a very elastic material where you have some load and you get the deformation. And because of the elastic property, it like rebound whatever load that is coming onto it. But suppose we have pressing it for a longer duration with more applied forces, and you get something like this deformation. So this is like appreciable deformation that will actually change the stiffness of this structure, or I would say this configuration, because the deformation is so large, the structure will change its behavior, like how it is transferring the forces. So that is why it is important to consider these kind of problems in the geometric nonlinearity. To light upon that thing, like how do we decide whether the analysis is linear or non-linear when you're getting some deformation? Because we get the deformation even in the linear phase as well. So how do we categorize them? So for that, like in linear geometric analysis, the deformation and rotation are smaller, and we can say like more close to 5% in the general aspect if we talk about. But in case of nonlinear geometric analysis, displacement and rotations are quite large. And even the small change in magnitude of force for nonlinear geometry can change convergence behavior considerably. So this is what we are implying, like even the small change in force after this point, like it has changed the deformations quite drastically, and the stiffness matrix will be changed a lot for this part. Coming to the second thing, that is the material nonlinearity. So the linear material is most simplified material type if we talk about, but that is not the general case. We actually idealize any material as the linear material, but obviously it follows some nonlinear behavior as well. So if we talk about the other type, that is nonlinear elastic, if the deformation is recoverable, and plastic if deformation is permanent. So this is the linear material type that I'm talking about. And the other type can be nonlinear elastic, where the deformation is recoverable. Like if you talk about this, where you are having the deformation that can be recoverable, it can be termed as nonlinear elastic, where the plastic, if the deformation is permanent. So where we don't have the deformation recovered, that is the plastic state that we usually talk about. So here you can see, like this is for the metals, the nonlinearity is occurring after the linear behavior that you can see from here. While for the different non-metals, if I talk about rubber or any other these kind of material, fabric material, so at that location, the nonlinearity is present within E itself. Like before, I would say the Hooke law is not applicable here, and it is nonlinear before that itself. The slope is changing at all point of time. And the other one is the nonlinear elastic and hyperplastic, where you can see this is the elastic plastic behavior, and this is elastic perfectly plastic, because we have having the stress is not changing while the deformation is changing. So if we talk about few major nonlinear material classification, it can be nonlinear elastic, hyperplastic. Example can be rubber material, linear elastic perfectly plastic material. So based upon these graphs, we can categorize how the material is behaving. And in FEA, if we put stress versus strain curve as material input, and the FEA calculates the deformation and calculates the strain for those deformation. So basically in finite element analysis, we put stress strain curve as material input, and then FEA calculates the deformation, and then it back calculates the strain for those deformation. And for this calculation of strain, FEA uses material stress strain curve to translate into stresses. So basically with the help of curve, we are getting the deformation. From the deformation, we are getting the strain, and from the strain, we are getting the stresses as per the curve. Coming to the third thing, that is the contact nonlinearity. So in contact nonlinearity, abrupt change in stiffness may occur when bodies come into contact or go out of contact. So suppose this is the case where you see like bearing is rotating for a mechanism, and at the point where it is in contact with this part, it will have more frictional losses and the stresses would be quite different. But when it moves to this location, the contact will be changed for the different part of this bearing. So that is how the stiffness and the stress distribution would be changing for this mechanical problem. And even if we talk about any civil example, so you see like I'm having a cantilever bridge, cantilever beam, where I'm having some prop support at this end, but there is some gap between them. So when a small deflection is taking place, it will act as a proper cantilever. But when it has the support from here, then it will be propped cantilever that have the that will have the distribution among the forces. So in this way, the stiffness of the structure will also change afterwards. So this is based on the contact nonlinearity. If we summarize the different nonlinearity that we discussed, so if our E, that is modulus of elasticity, is a function of deformation, then we can say it is material nonlinearity. While if our stiffness matrix is a function of deformation, then it is geometric nonlinearity that we see. And if our force is a function of deformation, then it is a follower force nonlinearity. So this is another nonlinearity that where the force that is coming is dependent upon the deformation. So another example of this will be P delta analysis, where the additional forces are coming into picture due to the deformation. So that will be the example of this. Then the last one is the boundary condition is a function of deformation. There, the contact nonlinearity. So that is how we can summarize the different types of nonlinearity based upon the situation. Now, if we talk about the nonlinear finite element analysis issues, because we as a researcher like face a lot of trouble dealing with these type of problems. So some of the major concerns that come into picture is like achieving convergence. So obtaining convergence is biggest challenge in nonlinear analysis, because it is more of a trial and error approach where we need to set the type of convergence solution that we want and the number of steps that has to be accounted. So the complex problems might require more load increments and many iterations at the each load step to achieve the convergence. Then the balancing expenses versus accuracy. So as we know, like if we talk about accuracy, like people would generally say like the more the iteration is done, the better and the fine accurate results we get. But that comes with an expense, like with that expense of software or with the expense of time, like how much time you are spending for the resolution of any problem. So that is the thing. So FEA involves expenses, solution time, disk and memory requirements, and more detail and finer mesh generally lead to more accurate solution, but require more time and system resources. So when we are dealing with any plate or solid elements, you can do as fine meshing as you want, but that will cost you the time and the software configuration that you are dealing with. Then a nonlinear analysis need additional iteration effects, both accuracy and expenses. And the another thing is the verification. So it is difficult to verify the FEA results due to increased complexity of nonlinear behavior, because software analyze what we are giving as the input. It doesn't know whether it is right or not. So we need to ensure whatever inputs that we are providing that are true and that holds like accurate for our analysis that we are approaching for. Then the sensitivity studies, mesh convergence, increase mesh density, reduce load increments, become more expensive based upon these verifications. Now coming to the main topic, like we have dealt as of now about the different nonlinear analysis that are present. Now we will be majorly focusing on the seismic analysis, like how the nonlinear analysis is important for the seismic analysis part. So before that, we start, what are the different type of seismic analysis that code recommends or that are present in the industry? So based upon the structure action, as we know, that can be elastic or nonlinear. And if we talk about the behavior of the force or the input that we are giving as a force, so that can be static or dynamic. The example of static force will be equivalent force method and the pushover method, where we give the load incremental in the static manner. While for the dynamic, we know that response spectrum and nonlinear time history, because here again, we have the modal participation ratios, and based upon that, the load is applied. And the nonlinear time history, we have the different ground motions, which are applied as a load to the structure. So that is also changing its time. That is also changing its value along with the time. So that is how we can categorize the different type of analysis based upon the action and based upon the type of load that we are applying. So if we talk about the in-depth detail, like what are the pros and cons of these analysis? So like people generally confuses why we are choosing a specific type of analysis for the problem. So that depends upon the requirement, like what is the thing that you are aiming for. So if I talk about seismic analysis, static seismic analysis, it is relatively simple to understand and apply and does not need rigorous calculation, and hence it is quick. Then the cons again for this part is it doesn't take into account the dynamic response of the structure, since this is a static analysis, and also the non-linearity of the material is ignored. So it doesn't lead to detailed response in earthquake. Then for the response spectrum analysis, it applies the dynamic equation of motion, and the different modes of excitation are considered, and also damping is considered while obtaining results. While if I talk about the cons, so the non-linearity is again ignored here. So it doesn't lead to accurate response. And also the way in which we are combining the results of response spectrum. There are different CQC, SRS methods that depending upon the type of combination that we are choosing, the results will be changed. Then the next is the pushover and the time history. So for the pushover, it is relatively simple to understand and apply. And here we also capture the non-linear behavior of concrete and steel. And we can also consider the P delta effect. The cons, if I talk about the dynamic equation of motion, is not considered, and structure is supposed to excite only in one direction or mode. Like we usually apply pushover in X or Y direction, or you can apply it for the dependent mode that is occurring. And similarly for the time history, like we have the nonlinear properties, and we also have the damping, and the dynamic equation of motion is considered. But the cons with that is it is difficult to understand and apply, and it requires a lot of additional parameters. So if we say about additional parameters, that becomes a ground motion, and the selection of ground motion for any structure is itself, I would say, a more in-depth research is required for that, like what type of ground motion we are choosing for a specific structure at that region. So that is again quite tricky to take over. Then as we discussed about these analysis, I would like to highlight like the pushover is more majorly based upon the capacity of the structure. While here we are applying the forces and then seeing the structure behavior, like we are applying the earthquake forces using the hazard curve or any response spectrum, we are applying those forces. Here, like you are using a ground motion, but in pushover analysis, we don't apply the known earthquake force. It is more like we are giving some controlled deformation. Like I want to see the deformation till 500 mm, how my structure is behaving. And we get the capacity of the structure, like how is behaving to that point of deformation. So we will talk more in depth about these analysis now. So the response spectrum analysis, if we talk about what is a response spectrum, so we must have studied this thing. Like a response spectrum is a plot of the peak or steady state response that can be displacement, velocity, or acceleration of a series of oscillators of varying natural frequency that are forced into motion by the same vibration or shock. So this is like one of the most simplest definition, I would say. Like suppose we are having a series of oscillator which is having different natural frequency, and we are applying a ground motion to that. So the whatever time period and frequency with which that different elements are oscillating, that gives us the plot. So based upon the time period of that specific structure, you can get the response, like how it is behaving. So the resulting plot can then be used to pick off the responses of any linear system given its natural frequency of oscillation. So this is the image taken from the code where we see the response spectrum for the different types of soil. Now, if we talk about how response spectrum is actually plotted, so the response spectrum obtained is usually obtained from uniform hazard, and it is currently specified in most design codes of the world. So to obtain the uniform hazard spectrum, the following steps is used. So this is explained in the Kramer book, where we have the seismic hazard curves corresponding to distinct spectral periods are obtained for a given site location. So suppose I'm having a site location, I will get the seismic hazard curve. So seismic hazard curve are nothing but we are having the spectral acceleration for a value, and then we are having annual rate of exceedance. Like for that spectral acceleration value, what is the annual rate of exceedance? Then a target annual rate of exceedance is selected for each spectral period, and the spectral acceleration amplitude is obtained. So here you see, like I'm having the spectral acceleration ordinate corresponding to each spectral period, and then it is plotted over here. So you see this is the graph between spectral acceleration at 1 second, while this is the spectral acceleration at 0.3 second. So I'll be using an annual rate of exceedance that can be dB or MC or any value that you choose. And based upon that, you will have the ordinate of the spectral acceleration that can be used in the response spectrum. So this is the concept behind how the response spectrum curve is obtained. Now, if we talk about the nonlinear static pushover analysis, so it is a technique by which a structure is subjected to incremental lateral load. So suppose this is my building, then I'm giving some lateral load toward it, and we are seeing the deformation that is occurring. So the sequence of cracked, yielding plastic hinge formation and failure of various structure components are noted at this location. And a building capacity curve is a plot of lateral load resistance offered by the building as a function of lateral roof displacement. And it is obtained as a plot of static base shear versus the roof displacement, which is known as pushover curve. So to simplify, like we are giving some monitor roof displacement, like how the structure is going under the cracking, yielding, and plastic hinge formation are done. And based upon that, we see the base shear that is coming onto the structure. So based upon this, we have the base shear and that displacement at the top location, which is nothing but it gives the capacity curve that is also known as the pushover curve. So if we talk about the pushover curve, so using the pushover curve, you must have heard that we get the performance point. So there are different approaches to get the performance point. One of the analytical studies is based on capacity spectrum method, ATC40. And here this method provides a graphical representation of the expected seismic performance of the building by the intersection of the structure capacity spectrum with the response spectrum. That will be the demand spectrum. So as I mentioned, like we are having the capacity spectrum from the pushover analysis, and we get the demand spectrum for that specific structure at that site. And the intersection point is called the performance point. So as I said, like it is not as simple that I say because to get this building capacity curve, we need to have the change in the coordinates of the value. So in order to have comparison with spectral demand, pushover curve is converted into capacity spectrum. So as you see here, like the pushover curve is having displacement and base shear as the coordinates, while the capacity spectrum will have the spectral acceleration and the spectral displacement as the coordinate. So we convert the static base shear is converted to spectral acceleration, whereas the roof displacement is converted to spectral displacement using modal parameters. So when we change that, like there is there are equations present in the code using which you can do this transition of the pushover curve to capacity spectrum. And it is, I would say, a linearized and a simplified capacity curve for a single degree of freedom. Because as I discussed, the response spectrum is for a single degree of freedom. Similarly, to compare this with my capacity of the building. So basically, I'm idealizing my building performance, which is multi-degree of freedom, which is having multi-degree of freedom, into a single degree of freedom. Because we get the pushover curve. And then if I idealize as a single degree of freedom, so that means the whole structure is actually following that single degree of freedom in the form of behavior, like how the structure is facing different deformation. So we get that curve, and this intersection point is known as the performance point. There are different methods as well for this, for obtaining the performance point. The other one is like where we have the different modification factor for the displacement. So actually the code, I would say the code idealized that we are having a deformation, and then we are adding different parameter or coefficient to have the non-linearity of the structure integrated with that deformation. Then coming to the next analysis, as we discussed the nonlinear time history analysis. So it is a step-by-step analysis of the dynamic response of the structure to a specific loading that may vary with time. So we obtain the median collapse capacity from this curve. Like you must have heard a lot of time that we perform time history analysis, but what is the output that you want from this time history analysis? That is what I'm showing here. We obtain the median collapse capacity, and a median collapse capacity can be identified as the intensity of ground motion at which half of the ground motion in the record set causes collapse to the structure. So this is as per FEMA, like we are using incremental dynamic analysis where we are having the ground motion and we give the scale factor to that correspondingly, like till it reaches the collapse point. And a collapse point can be another debate point, like you can choose the different methods to has your intensity measure. So in this case, like you see maximum story drift ratio. So suppose I'm applying a ground motion to my structure and it is following some graph and it is having some drift ratio for the different spectral acceleration. But suppose I've given a scale factor of 3, 4, 5 and it is reaching till this point. But in the case when I give the scale factor as 6, the maximum drift ratio has increased drastically. So I would say the collapse of the structure is coming into picture for that scale factor that will give us the spectral acceleration. So that will how you will do for the different ground motions that are in the record set, and accordingly you perform the time history for that. So we do that for all the ground motion set and we obtain the median collapse capacity. So now you can understand that like median collapse capacity can be defined as the intensity of ground motion at which half of the ground motion in the record set causes collapse to the structure. So we understood what is the collapse of the structure. Suppose I'm having 22 ground motion for which I'm performing time history. So median collapse capacity will be that where half of the ground motion is causing the collapse of the structure. So that is how you can obtain it. Then after getting it, we can obtain the fragility curves as well. So based upon the Hazu's methodology, it can be used to develop the fragility functions. And according to Hazu's, the fragility curve follows a log normal distribution representing probability of exceeding a particular damage state and is given as this equation. So if I brief about this equation, this is the probability of collapse for the specific spectral acceleration that for which we are checking. And it is a function of logarithmic where we uses these values. So SCT is median value of spectral displacement at which the building reaches the threshold at damage ds. Or we can also convert into spectral acceleration. So this will be the median value of spectral acceleration where it reaches the threshold value, which is nothing but it will be this median collapse capacity that we are talking about. Then we have beta, that is the standard deviation, and it considered two type of, I would say, deviation. One is the modeling part and other is the record to record variability that is coming in your structure. So based upon the ground motion, you will have the record to record variability, and another is the modeling deviation that can be considered here. And phi is the standard normal cumulative distribution function. So based upon this, like you have the graph of probability of collapse and spectral acceleration. So this is the curve that I obtained in my research study for different zone, like this was for the zone 4 and this is for the zone 5. So if you see, I'm having zone 4 in this orange color, And for the different spectral acceleration, it is lying above this blue curve. So the reason is quite simple to understand. Like for my zone 5, the hazard curve value that I take, like the spectral action that we take, MC value, that is more for the zone 5. And that is why we design the structure for higher forces. And hence the probability of collapse is lesser for that curve, because the same building was used in the modeling. So that is how you can understand how these are varying. So to understand it, like we get the spectral acceleration, and according to that, you get the probability of collapse for your building. So that is how the time history analysis results work. And I will showcase some values and some sheets as well. How do we calibrate that in the later stage? So this is the median of idea, like this is the dynamic capacity curve, which I had performed for the building model 1, which was for the zone 4, and this is for the zone 5. So this is just to give you an idea, like I had this different set of ground motion, which was far field set, and I choose 22 ground motions from the code, and I had the idea performed. And you see, like for these ranges, you can see how the maximum interstory drift ratio is quite increasing drastically for the spectral acceleration. So we get these curves first, and from here I get the median collapse capacity and record to record variability. So this is something which is obtained from the data that we are using, and seismic demand at fundamental period was shown, and the collapse margin. So collapse margin ratio is nothing but is the ratio of median collapse capacity and the seismic demand at fundamental period, which is this. So it gives me collapse margin ratio as the name suggests. If I talk more about it, like how do we obtain this? So this is the Excel sheet that I used. I hope you can see this one. Yeah. So like I had the different scale factor, and these are the different ground motion that I was having 1, 2, 3, 4 in this manner. I performed it for different ground motion, which you can see there are 44. Like the total record set was 22, but we applied it in the both the directions since the structure was not geometric. So I applied in both the transverse direction, and then I had the different scale factor. So you see, I plotted a graph between the scale factor, and I would say the graph is plotted between the spectral acceleration and the interstory drift ratio that we are having. So you see, when I'm choosing the scale factor as 5, 10, 20, and 25. So based upon that, you can see how the IDR is changing. So till the point of 25, this was not appreciable. But for the scale factor of 27, this value has increased drastically from like it was second decimal place to come into numerical integer value of 4.25. So that is how you see a drastic change for this scale factor. So I can say for this spectral acceleration, the collapse is occurring for this specific ground motion on my structure. Similarly, for other set of ground motion, we perform the same thing and we obtain this graph. Once this graph is obtained, then we have this sheet where I can just tabulate all the scale factor and the spectral acceleration that I'm having. Then I will calculate the logarithmic value, and the median spectral intensity will be this. Like I'm choosing the median of these 44 values. This was coming as 0.22, and then the beta. So this is record to record variability. And we choose the standard deviation of this. So that is 0.314. Once I obtain this, I can make the fragility curve where I'm having the different spectral acceleration, and I can get the probability of collapse for different spectral acceleration. So this is the SA median that was calculated, and this is the record to record variability, but this is beta corresponding to the modeling one. And then we have these values to obtain the graph. So today, like we will be majorly focusing on the pushover analysis, but I wanted to give you an overview about the time history analysis as well, like how do we perform that and what are the different results that we obtain and how we achieve the final conclusion point with that. So you can see, like this is the equation that we used, and the median collapse capacity for the zone 4 was 0.23 that I calibrated, and for zone 5 it was 0.3. Then the total variability, and total variability, if you see, like this is a value which is considering record to record variability that we obtain from the ID of the buildings, and the value of modeling uncertainty, that is beta m. So it is obtained from Hasselton and Derlin 2007, where the value is taken as 0.5. So it is This beta t is nothing but the under root value of square of this beta modeling and also the beta record to record variability. So this can be used here. Then we actually calculated median collapse capacity using IDA, which is SCT, like this will be SCT. And then when I give the different values of SA, based upon that, I will get this probability of collapse. So that is how we perform it. Now, since we have discussed about different seismic analysis, it is critical to know like which seismic analysis is to perform for your building. So if we follow IS 1893 part 1 2016, so it clearly divides like what for what part of structure, like for what type of structure you can use the equivalent static method, that is linear static method, and for what type we need to shift towards the dynamic analysis. So here you see this method shall be applicable for regular buildings with height less than 15 meter in seismic zone 2. Can someone mute themselves, like there is some background noise? Okay, thank you. So yeah, the equivalent static method, it shall be applicable for regular buildings with height less than 15 meter in seismic zone 2. So these are the general structure for which you can use the equivalent static method. If we talk about it as per this method, the design base shear is computed for the building as a whole, and this VB shall be distributed to the various floor level at the corresponding center of mass. And like we first calibrate the total base shear value using this formula that you can see. And the AH is the design horizontal acceleration coefficient value, while W is the seismic weight of the building. And this can be calibrated first. The value of AH can be taken from the codal value, where it provides the time period and the corresponding spectral acceleration for the different height of the buildings that you can use. Once you calibrate VB, it will be divided into different floors. And again, in the floor, like we will have the diaphragm action. So the design seismic force at each floor shall be distributed to different, or I would say individual lateral load resisting elements through structural analysis, considering the floor diaphragm action. So by floor diaphragm action, we mean that there is a rigid action among all the elements of the floor, and there is no, I would say the deformation is not coming, and the force is properly transferred to all the horizontal components using this diaphragm action. So this is about the equivalent static method. Then the code specifies for all buildings other than regular buildings lower than 15 meter in seismic zone 2. So suppose your building height is more than 15 meter, then in that case you need to opt for dynamic analysis. And even suppose your building is in zone 4 and it is of height 10 meter or 12 meter, then also you need to perform the linear dynamic analysis. So as of now, we are shifted from static analysis to the dynamic analysis. And based on the material configuration property that we are using, it can be linear or non-linear. So dynamic analysis may be performed by either time history method or the response spectrum method. So the time history will be non-linear dynamic, while response spectrum will be linear dynamic. When either of the method is used, the design base shear VB estimated shall not be less than the design base shear VB calculated. So this is an important thing that code mentions. Like we calculate the VB using this equivalent static method, where we have the fundamental time period from the code itself, where we calculate the VB. And suppose you have performed the response spectrum directly in the software, but the base shear that you are getting for the response spectrum, in case it is less than by the VB that is calculated from the code, then you need to multiply your force by the factor of the same values. So suppose I'm having a base shear of 1500 as per the code, while I'm having a base shear value of 1000 kilonewton in my analysis software. So that gives me a factor of 1.5. So whatever values that I'm having, I need to multiply it by 1.5. So what I can do, I can just change the scale factor and multiply it to 1.5. Accordingly, the effect will be changed for all the forces. So now we will be talking about the modeling things that are to be considered, and then we will move towards the demonstration part. So the model that we will be modeling today would be something like this. I'll have a G+9 building, and the 3D frame elements will be used for modeling of beam and columns, and the roof or slab will be modeled as the rigid diaphragm. We will, like, as per the codal provision, we need to ensure the strong column, weak beam. So this is nothing but it is a capacity design as per IS 13920. So it suggests that the column should have more strength than the beam. And this is the reason, like when we are dealing with earthquake resistant building, the concept behind is that whenever there is a mechanism form, the column should be safe during the mechanism. The mechanism should be first formed in the beam rather than the column, so that you will, like you have seen different limit, immediate occupancy, life safety, and collapse prevention. So these are the different limit that the code specifies. So if I talk about it, suppose my column is failing at first, so the life prevention would be quite, the collapse prevention would be quite difficult for this case, because if the column is failing, it will make the whole building to fall. But if suppose for any different type of floor, we are having the mechanism formed in the beam, then it is okay. Like then we can say that it has not reached the collapse prevention stage as of now. So that is the concept behind that. Then we can also consider the P delta effect in the analysis itself. That will give me the second order forces that are coming due to the deformation. Then another thing is about the effective stiffness of RC frame members that are to be considered. So there are different stiffness modifiers given in ASC 4113 that can be considered. So you see, if your beam is non-pre-stressed, you will be using the flexural rigidity of your beam as 0.3 ECIG. So you will not be using the total stiffness, but you will be using the effective stiffness here, because since we are dealing with non-linear thing and the analysis, like we are seeing that there might be crack properties that are coming into picture. That is why you are using this. And as per IS 1893, the moment of inertia shall be taken as in RC and masonry structure. For the column, it will be 70% of high gross, while for the beam, it is 35%. So it is quite similar. Like as per ASC, it gives 0.7 for this value, and the IS 1893 gives 0.7 again. But in ASC, like you will find that it has given two values. Suppose your axial force that is coming on the column is more than 0.5 Ag FC dash, where Ag is the gross area and this is the characteristic strength. It is more than 0.5, then you will be using this. But if the columns with compression caused by design gravity load is less than this value, then we'll be using this as the flexural rigidity. Then the next important thing is to talk about the hinges. Since we are dealing with nonlinear analysis, so how do we incorporate the nonlinearity in the model? So hinges are the answer for that. Like there are two approaches available for nonlinear modeling of RC frame members. So basically we can assign the hinges via two approaches. The first is the lump plastic approach and the other is the distributed plasticity approach. So these are nothing but these are the type of hinges that can be used. So if I talk about the lump plasticity approach, here the inelasticity is lumped at the ends of the elements. So basically what we are suggesting here is, suppose I'm having this as the beam element, we are assuming that yielding is assumed to take place only at generalized plastic hinges of zero length, which are these location. And other than that, the linear elastic members are assumed between these hinges. So I want that nonlinearity to be modeled. So in lump plasticity, I am assuming the nonlinearity is taking place at these locations while the linear model is present in between. So this is for the plastic approach where you will have these hinges defined. The reason we are choosing it at end or at the connections, because this is the location where hinges are generally formed and the mechanism is observed. So that is the reason to provide it in that manner. Then the second approach is the distributed plasticity approach. So here inelasticity is distributed along the length of elements that you can see, and yielding is distributed over a finite length of these members. So a fiber section is an example of that, like a fiber section that we are providing at these locations, different location. So in today's model, like we will be using with lump plasticity approach only. So if I talk about what type of hinges do we need to assign to the beam and column. So here you see, like for the inelastic modeling of RC frame members for beams, moment rotation hinges that are M3. So we had the backbone curve of the moment and the rotation. The moment is corresponding to M3 and the rotation that is observed. So these hinges are assigned at a relative distance of 0.05 and 0.95. So this is for today's model that we are doing. And these distances can vary, like you can also give at other distances. Then the backbone curve for force deformation curve properties can be taken from ASC 4117. So whatever backbone curve that we are using, we need to ensure that is properly considered for the analysis. Then for the columns, so columns are biaxial members. That means like the bending is dominant for both the direction, but these available backbone curves are based on uniaxial test results. So because that is the main reason that you must have seen like fiber hinges are used. So in case of columns, we will be using the fiber hinges. So if we talk about fiber hinge, so in fiber hinge, we are having this RC cross section that you can see. I'm having the column, then these are my longitudinal reinforcement and the transverse stirrups that I'm having. So I will have the both the properties, unconfined concrete fibers at the end, whereas the confined concrete fibers at the middle, which is inside the stirrups. And then I'm having the rebar fibers at these locations. So basically we are discretizing all the column elements into different parts, and we will be assigning the nonlinear properties to these material. So for the concrete as well and for the rebar as well, you will be giving the nonlinear property to the material, and that will induce how your structure is behaving in the nonlinear range. So that is the difference between the two. Here, like in this rotation curve, I'm directly giving the backbone curve. According to the deformation, the moment will be calibrated, or like based upon that relation, the nonlinear hinges will be performed, will be like followed up. While for the column, we will have the non-linearity based upon the material. Like each material is assigned for the different elements, and then the non-linear behavior is captured. Now coming to the structure that we are modeling. So this is the detailed plan of RC frame building that we are having. So I'm having a span of 6 meters in the longitudinal direction. The number of spans are 5, making it a total of 30-meter long building, 30-meter in the longitudinal direction. While for the transverse direction, I'm having 5-meter span, and there are 4 span in this location, making a total of 20-meter of the span. Then here you see the sectional elevation of the building. So at the bottom, we will have 1.5 meter as that can be treated as the foundation. And then we will have the ground floor and the different stories. So we will have the 9th floor, which will be this, and you can say it as Z plus 9 for the modeling purpose. Then the different overview that we are doing. So for the general bare frame design for gravity and seismic action as per special moment resisting frame. So you must have encountered with these names where the OMRF or SMRF terms are used. So SMRF frame are nothing but these are the element that are designed as per the special provision for the earthquake resistant design by following the code. Like the detailing, ductile detailing is done as per the 13920 and 1893, while for the ordinary moment resistance frame, we don't use that. So the number of stories, it is 9-story building. Then material for the concrete, I'm using M40. For the steel, it is Fe500. Then the dead load that we are considering. So we are just using the simple superimposed loads, that is like the self weight of the member, weight of infills, and weight of slab and floor finish. And then we will have the live load that will be 3 kilonewton per meter square applied for the slab. Then if we talk about the different structure modeling, so the structure will be modeled as the 3D frame and elements of beam and column. So if you talk about finite element analysis, there are different type of elements that can be used for the modeling. It can be either your frame elements, truss element, plate, shell elements. So based upon the requirement, we choose what type of element we want for the analysis. If I talk about the industrial approach, so generally the frame elements are majorly used, but when we need to deal with some finer accurate results, where we are talking about some steel connections where you want to see how the stresses are behaving, at those locations we use the plate elements. While for the research purposes, we know that we go in depth with the analysis and results, because for the research purpose, the behavior of the structure is quite important to understand how it is behaving. So that is why you use those higher end elements for the research purpose. Then we have the plasticity models to have the nonlinear behavior. So as I mentioned, we will be using lump plasticity model based on chord rotation for beam and fiber hinges for column. Then there will be stiffness modifier used for the column and beams as per AC 41, P delta effect, and support would be fixed. So now we'll be moving towards the demonstration part, and you can open your ETABS window. So from here, I can create the new model. And I will use the settings for the metric and Indian standards. So you can use these values. And then click on OK. Then it asks us about the grid. So I'll just wait for a couple of minutes so that everyone has reached this state, like they have opened the ETABS window, and then we will define the values of the grid.
Okay, sir, we have opened the ETABS.
Okay, great. So like from here, we can set the grid, whatever grid that we are having. So I'll be like, you can use the custom grid spacing as well. But for this case, like I'm using this uniform grid spacing between the two. So I'm having number of grid lines in X direction as 6, while in the Y direction, that is 5. Then I have the spacing grids in X direction as 6 meter. And for the spacing of grids in Y direction, that is 4 meter. So if we check the grid labels, like you can select what type of grid you want for the X grid and the Y grid. And from here, we will give the number of stories and the typical story height. So I'm having 10 stories and the bottom story height is 1.5 meter. That will simulate my foundation. And accordingly from the ground floor, I'll have 9 stories. So we give that values. And once this is done, I can click on OK. So you will see 2 tabs like that has been created. This is for the planar view, while this is for the 3D view, which we are having for the element. And now we need to define the different properties. Like as of now, you can see I'm having 6 meter grid at this location, and here I'm having 4 meter for the different element. So we start with the definition of the material and material properties from this location. We click on this. Just a minute. Yes. So these are some previous materials that has been defined. We won't be using that. So we will be defining a new material. So based upon the region, like you can select the different code. So I choose the region as Indian, and from the Indian, like I'll have the material type first. So that will be the concrete. And from the grade, I can choose what grade I want to use for my material. Suppose I use M40, I click on OK. It will give me the properties of the material that I'm using. So as you see, like you can choose whether the material is isotropic or orthotropic. Material type is concrete for me. Then we have the density and mechanical properties, modulus of elasticity and everything. And from here you choose, like we have the non-linear material data. So I can click on this option, and we have the option to have different acceptance criteria and the different stress strain curve that we want to use. So as of now, like we will be using the Mender model. So if you drag and you see like there are different models that are present here. As of now, I'm choosing that value, and later on we can edit this value as well. So as of now, I'm just choosing this. If you see the show stress strain plot, so you will see this value. So since this is a concrete material, so we know like this is the compressive stress that is going for the corresponding strain. And from here, like you can choose like this is your yielding point, and accordingly you can select your immediate occupancy, life safety, and collapse prevention. So this will be the collapse prevention, I can say. Based upon this, you can choose the strain values as well. And this is for the tensile region, where you see the stress is quite limiting to, I would say, around 1 megapascal. That is for the compressive values. So once this is done, I can click on OK.
Mr.
And
Mihir,
Yeah. Mhm.
There is a question that if we want to change the units,
Mhm.
then where to, which option we need to go for in order to change the units?
Okay, yes. So for having the units, like at the bottom right, you will find this option for the units where you
Okay.
have all these values and you can choose this show units form. So while using this, you will have the units that are used for all the different properties. So if I want to change it, like suppose I'm changing the acceleration value. So that is time related value. So I would recommend like everyone just can go through this unit form, and I will change this acceleration value to meter per second square because we are more familiar with those units. So I'm using that value over here. Apart from that, I'm keeping it as default, and you can see like it is metric system as of now that we are using. In case you have some other units, like you can just choose this metric SI defaults instead of US defaults. So we were talking about the materials. We have defined M40. Similarly, I will be defining the rebar that will be used. So here you will find the material for steel as well and for the rebar. If you go to the steel, you will find the different Fe values. While you go to the rebar, you will find the different grades that we usually deal in today's industry like Fe 415, 500 or 550. I will be using 500 and I click on OK. So this will again open the property of my material. I will also see some questions meanwhile, like in your plan, the grid is of 5 meter length in Y direction. Yeah, like in the initial, like I had the model that was of 5 meter, but that in this demonstration, like we are using 4 meter. So that is okay. Like you can use this 4 meter values itself if you have inputted that. Then if I talk about why select ETABS, why not MIDAS Gen or Engine? So since I'm like a MIDAS employee as well, so we use that for the building analysis as well. But the reason of choosing ETABS was because more of the students are familiar with the ETABS. That is why we chose this software. And then can you explain again the non-linearity of concrete and waste hysteresis loop? So, okay, I'll just define this one first. So we have the HYSD. I click on the non-linear material data. And from here, I can set the values that I want to use. So So here you see like the different acceptance criteria. These are immediate occupancy, life safety, and collapse prevention. If I say talk about these acceptance criteria, the immediate occupancy is the stage where we are not having much deformation or the strain in the structure. And after there is some, I would say, earthquake event, the structure is quite suitable to use again immediately. While for the life safety, there are some deformation and there is some structural damage. But in IO, there is no structural damage. But here in the life safety, you will see some structural damages are coming into picture, but it will be in the life safety region. While in the collapse prevention stage, you will see a lot of cracks being developed and the structural components being damaged, but the collapse is restricted, like the columns are standing and the collapse has not happened for your structure. So based upon this, like you can give the tension and the compression values as well, like for the strain, what are the values that could be considered that can be provided. And if I talk about this value, so this is for the HYSD 500. So I had the simple model. If I convert it into user defined, so you will have the strain and stress values for the different parameters for the different points that could be used. And here you see the hysteresis type. So it can be kinematic, isotropic degrading. Suppose I choose that as degrading. Then I can choose these values, like how the energy factor and parameters can be considered from here. And these can be used from the past research or from the codal reference that you are performing the analysis with. So once this is done, I click on OK. Similarly, if I talk about M40, so hysteresis type, suppose I choose as degrading again. Then you have the values to be provided for the tension compression parameters that can be provided from here. So this will have the hysteresis curve, like how the degrading and the hysteresis slope is being formed for your concrete. And if I talk about the stress strain curve that we are using, so if you convert into the user defined format, then you can see the different plot of it. Like the negative value is actually shown here as the compressive values and the corresponding stress. And this is for the tensile region that you can see. So if I talk about M40, like you can change this values as of now, like we are having compression at 0.003. So based upon this, if you just cross check like the stress strain curve that you are having. So you see like this is my IO value as of now, which is 0.003, while this is a life safety, while the collapse prevention is somewhat two way ahead. So I can change this value. So I will make it as 0.0015. This as 0.003. This is 0.006. Now you can see like how, like this is the IO level, life safety, and this is a collapse prevention. So that is how like you can choose what type of strain you want for your material for the different occupancy. As of now, I'm taking these values from the past studies that we have done. Once this is done, I click on OK. So again, I can define another material. Which will be HYSD grade 415. That can be used for my stirrups. So I'm keeping these values as default for now. We will, if required, we will change it at the later stage for now. As of now, we have just changed this M40 value that I will show again. So we change this IO value to 0.0015, then LS as 0.003, and collapse prevention as 0.006. Then I click on OK. So as of now, we have defined the materials. Now the next thing is like we can define the section properties that are to be used. So for that, I go under the define option again, and I will be using the section properties from here. So I go to the frame section, and there are some previous sections that are defined. I can delete the multiple properties. And I will be defining new property for my beam and column. So when we click on add new property, you will have these different options like what type of section shape that you want. We will be using the concrete one, which is this. And I can give the name as beam. Material will be chosen as M40. Then from here, I can give the depth, that is 400. And the width is 300. This will be updated. Then I can choose the reinforcement from here. So you see the design type will be M3, design only beam. Since we are dealing, this is the beam section that we are defining. And here I can choose the rebar material that I want. So for the longitudinal, I'm using HYSD 500, while for the confinement, that will be my transverse stiffness. So for that, I'm using HYSD 415. Then I will give the cover to the longitudinal bars as 40 mm. And I can click on OK. So I've dealt with the reinforcement again with the property modifiers. Then here I can use the moment of inertia about axis as 0.3 M3 because we are changing that value for the beam as discussed in the presentation. Like I will be using a stiffness modifier. So I'm giving that from here. I click on OK. You click on show section properties. The area, moment of inertia, and the location of centroid, everything would be shown here. Once this is done, we click on OK. So our beam has been defined. I'll be just deleting the other sections. So I just have the beam section, and again I use the other one. So I add new property, and for the concrete, I give the name as column. Choose the base material, that will be M40, and give the sectional dimension. So I'm using 400 cross 400 for my column. Again, for the case of column, we will be having the design type as PM to M3 design. The reason we use this design type is because the beam is going bending under this axis only. There is dominant bending for M3. While in the case of column, if you talk about the capacity of a column, so it is dependent upon the axial forces and also the bending in both the direction. That is why, like in the case of beam, you will have the capacity design only for your flexural capacity like this. But for the case of column, you need to consider what are the combination in which the axial forces and the moment is occurring in the element. So that is why we are choosing this PM to M3. Then from here, I can choose the rebar material again. And I'm using this cover as 40 mm and these values as the default for now. So if I click on OK, like this is the default I'm having. From here, you can set the reinforcement that is having. So the number of longitudinal bars along 3 direction face, that is 3, which is this. And the number of longitudinal bar along second direction face, that is 5. So this is like, if I talk about direction face, this is second face in this direction, while this is 3. So for the 3 face, there are 3, while for the phase 2, there are 5, which is shown. Then the longitudinal bar size, so I'm using 20 mm. And for the corner bar size, again, I'm having 20 mm in this case. So the EST is calculated for that. Again, for the confinement bars, we are having the size of 10 mm. So these will be the values for the transverse reinforcement that will be having for the shear. And it is of 10 mm size and the area is calculated for that. And the longitudinal spacing of confinement bar, like these are placed at 150 mm distance. And then the number of confinement bar in 3 in direction 2. So those are 2 seen. So once this is done, I click on OK. I see in one of the messages a question about this include automatic rigid zone over column. So basically that implies that the casting of the beam and column is done properly, like all together, and the whole width of the beam that is coming on the column, it is acting as the support. So based upon the detailing that you are doing on site, like if the reinforcement or the development length is properly transferred to the column for all those width, then it means I would say then it means the support is provided to the beam along the width of that beam that is coming on the column. So then in that case, you will choose like the include automatic rigid zone over the column. So once this is done, I click on OK. I have defined the beam and column for now. Then next we will be defining the different elements that are for our grade. So you can have the different definition options using these values on the left side that you can see. From here, you can select the object, and from here you can draw the beam and element. If I talk about the user interface, like as of now, we have defined the material and properties. So the user interface is quite friendly. Like we can define all the parameters from this phase. Then you have the viewing options here. You can edit any grid or material or frame that you have defined via this. Suppose you have defined the frame for 6 meter span, but in case you are adding some secondary beam here. So a primary beam is that where we are having the support along the columns, while the secondary beam is somewhere which is having the supports at the primary beam. So suppose I'm having a transverse beam here, that will be the secondary beam. And for that, I can just divide the frame in to get the nodes, or in that manner, you can make the modification. Then we have the select options where you can select the different elements and the object based upon the different properties. Suppose I want to select all column, I can choose the object type and I can choose it as column beam, and accordingly all the elements would be selected. Then I'm having the assign option. So from here, we will be assigning all the frame elements, all the links, and all the, I would say, the different frame loads that are coming. That will be assigned from here. Then we analyze the model, check the display results, and then we can perform the design. And these are the miscellaneous option. So this is how the workflow would be like. And these are some shortcut tools to select and activate different elements. This is the model window where you will see all the inputs, whatever you have provided for now. So the materials that I provided, you can see here for the stories that we are using and the grids that we are using. In case you want to edit the grid, you can just go to modify. And again, as mentioned, like this was shown as 5 meter for our case. So let's change this values to get like more appropriate thing that we were talking about. So I would recommend like you just go in the model and under the grid, just right click and modify show. And here I can change the coordinates and I click on OK. So these are updated automatically. So just to give you another glimpse, like how you can make any modifications as well. So once this is done, like now we will be assigning the frames. So I go to the assign frame option. Like from here, you can give the properties. As of now, I'll be using this quick options. So using the draw, like we will be drawing the beam by selecting these points. And like in this manner, I can do. As of now, I'll just select and delete this element. And the other option is like quick draw beam, where you just need to select these in this manner and the beam would be drawn. Again, I'm just using Control Z to undo these definitions. And the most easiest way, like from at the bottom right, you will see we are having the option of one story and you can choose it as all story. So I'm using all story because whatever things that I'm doing in one will be shown for the all stories. Now, yeah, we don't have any beams, so it is okay. Now we will be selecting this quick draw beam option and I'll just drag in this manner. So that will give the input of the beam for all the different forces, all the different stories in a single go. So that makes the work quite easy for me. As of now, like it is easy because we are dealing with a simple geometry and we are using the same sections. But when we are dealing with industrial projects, the beam sections and beam sizes are also quite varying. And also the detailing that you are providing will also vary. So then in that case, you will be using different section and assigning those at the different levels. Now the next is the column definitions. So I can use this quick draw option for the column. And on the similar manner, I can just drag in this way to have my column defined. So one of the important thing that we missed is here, like while defining the element or assigning the section, we need to see what type of property is being used. So as of now, you can see, I got to know like I am doing it wrong because my column was having symmetric sections for both the directions. So I'll just undo this thing. So these are removed. And if I want to check this section, what has been assigned. So section property of beam is assigned. So that is okay for us. Now I choose column and I will be choosing this property as column here. And I'll just drag and drop like this. So the columns has been assigned for all the section. Please explain about giving the torsional constant in frame element. So if I talk about the torsional constant, so we can keep it as 0.1, like By the torsional constant, we means whether because during the analysis purpose, we don't consider that the detailing is done in that manner, like it is actually giving all the load to the slab. So this is the torsional constant. Suppose I'm having slab. As of now, we are not modeling slab, but when we are modeling slab and we want to ensure that the moment are not transfers to the beam, because that is the general approach that people use. So they give the torsional constant as 0.1, so that ensure that there is no development length provided between the slab and the beam, and the torsional moments are not, because the torsion value that is for this, that will be the bending for the slab that is coming above it. So that is why we can keep it as nominal value so that it is not transferred. But as of now, like I'm not dealing with the slab elements, we will be using the diaphragm action. So it wouldn't matter much. So maybe you can like, as of now, keeping it as one itself. So that is the significance of it. I click on OK. So yeah, we have defined the frame and the column and the beam. Now the next part is the support, which is at the end. So what I will do, as of now, I'm at the story 10. So I can just go into the different stories by doing this option. You can see how the stories are changing. This is the base story. So now I will want to apply the fixed supports at the end. So I will choose this as one story because I don't want the support condition to be applied for all the nodes when I select these points. Now we'll be using this select option and using this. Now only, like you can see, only the bottom nodes are selected. Using the shift and the scroll button, you can rotate this model in the 360-degree view. And while using just scroll, you can pan in this manner. So now I define, like I go to the assign joint to the restraints. Okay, yeah. So these are the different restraints. So here you can find the hinge condition, pin condition, and the fixed. I'm using this as the fixed. So all the degree of freedom, the translation XYZ and the rotational XYZ, all are fixed. And I click on apply. I click close. So you can see it has been applied at the bottom. In case you are not able to see these restraints, like here we go to the display option. And we are having the different visibility options, like what type of properties you want to see over here. So as of now, like if you see the joint restraints and springs, this is check on for me. If I check off this thing, I click on apply. Just a minute. Okay. We go here and then we choose assign, clear display of assigns. So now it is removed. Basically in the last step, whatever assign that I've given will be shown by default, and that can be chosen off by going under the assign and clear display of assigns option. So now if you see here under the check option, now I check on this thing and I click on apply. So now it is shown. So that is how you can see that. Sir, what is your opinion on fixed or pin support? How you choose fixed support to be assigned? So as mentioned, like it depends on the type of soil, but I would also say like we generally, if I'm using this type of foundation where you see I'm having a depth of 1.5 for my foundation. So I wouldn't be giving it in the property where I'm not having the hard soil or the support is not fixed. I might be using pile foundation or raft or mat, something like that in case I'm having some cohesive soil at the bottom. So then in that case, I might give the soil properties as well, like what is the stiffness of the soil, the coefficient of subgrade reaction. So those things can be used for the definition. So as of now, we are using fixed because we are assuming it is on the hard soil. So next thing, like we have given the support. the thing that approach I'm following is like, first we have created the material and the sections, we have creating the whole model now. Like I'm having the frame elements, I'm giving the fixed condition, and then I will be giving the diaphragm because I'm not modeling the slab, but I will be giving the diaphragm for the different floors to have that rigid action that is important for any earthquake or seismic analysis. So for that, we go to the define option, and here you choose the diaphragm option. So as of now, you will find a default diaphragm that has been defined as D1. I click on modify show. And when I see this diaphragm D1, rigidity, it is as rigid. So I'm not defining any new, but you can define a new diaphragm again via this approach. I click on OK. Now I need to assign this diaphragm at the different location. So if I suppose I choose the elevation view in this manner, and I select these nodes. I'm not choosing for the last one, and then I go to the assign joint diaphragm. So from here, I will be assigning the diaphragm D1. I click on apply, click on close. So now if you see the 3D, okay, basically like this was chosen as one story. So only the extreme nodes were selected. So I'll choose that again as, I'll do that as undo. Now I'll see like whether these are selected or not. These are not selected directly from here. So likewise, maybe like we can assign it floor wise as well. Or you can select in 3D manner in this way. You need to be ensured like the bottom nodes are not selected here. Once these are selected, then I go to the assign. So now you can see the diaphragm that has been assigned at the different floor levels. So at times, like when we are having different levels, the diaphragm definition can be tricky. Like there can be, you are selecting the nodes from the bottom floor are also selected. So it is important. You see. Okay. Yes. So I was mentioning like all the nodes for the similar floor should be selected for the diaphragm. So we need to ensure that thing. In case that is not the case, you are facing trouble. So what you can do, you can just go to the plan wise option here. Suppose this is for the story one, I can choose this as one story, and then I can select the nodes over here. So you can see in the 3D that only the nodes for that floor will be selected. So this is the another approach for that. Okay, so I go to the assign and I clear display of assign. So you don't want to see these diaphragms. Yes. So we have given the diaphragms as well. Now, like we can define the load cases and the load pattern that are for our structure. So for that, we go to the define load pattern option. And here I'm having the different dead load and the live load for now. So I'll add new load. Like I'll give the new name, apply dead load. Self-weight factor will be kept as 0. This will be used for defining the different superimposed loads that might be having, like the I would say the infills brick workload that we want to apply. And then I can have EQX. That will be the response spectrum function if you want to define, like we can also define that here. And you can choose the type as seismic, and then you can choose it from the code itself, or you can choose it as none and later define as a function. So as of now, I'm just defining it for, say, earthquake in Y direction. And I choose it as none and I click add new. So only for EQX. New. So we have defined this load patterns and I click OK. Just to go through that again in case you have missed on any of the step. Like we have already had the dead and the live load. I had just added applied dead load under the type dead and the EQX and EQY. Later on, I'll define the pushover as well. So I go to the load cases now. And here you will find all the dead load and the live load that has been applied in this manner. Modal analysis will also be done. So under the EQX, EQY, later on, you can set the response spectrum functions and define that. We will do that later on once we define the functions. As of now, we will start with the application of the dead load and the live load. And before that, like for the pushover analysis, we'll also require a gravity load where all the dead load are considered and a percentage of live load. Based upon the intensity of live load, we have the percentage. In case it is more than 4, then we use the factor as 50%. In case it is less than 4 kilonewton per meter square, we use it as 0.25. So I'll define a new load case. That will be for the gravity. It will be nonlinear static type. Mass source will be mass source 1. And I will be adding the different load pattern that are to be considered. For the dead load, similarly for the live, I will have the factor as 0.25. You can consider the P delta geometric nonlinearity as well here. Once this is done, I click on OK. So I'm having the definition of the gravity. I click on OK. Now I will be assigning the loads to the frame elements. So I go assign frame. We go under the assign and here you will find the frame loads. I want to apply it as a distributed load. So I want to apply it to all the beams. So I can just go under the select. And I can choose object type as beam. So all the beams are selected. And I can give the intensity. So for the applied dead load, I want to give a UDL intensity, which is 12 kilonewton per meter. So suppose I'm choosing I would say density of my brickwork is close to 80, and then we have the mortar that is like for 100 mm, we have the density of 20 kilonewton per meter cube. Suppose we are choosing an average value of 20 kilonewton per meter cube for my brickwork, and I'm applying it for the breadth of my wall is 200 mm. So I will have that as 20 into 0.2 and the height of the building is 3. So I have a UDL intensity. So that will be 12 kilonewton per meter that I'm applying. So I select that and I click on apply. Direction of gravity, like the direction of load application, you can see it as gravity and you can see how it has been applied. Similarly for the live load, suppose I'm choosing trapezoidal distribution of the load case, then you can find the intensity of the live load. There is 3 kilonewton per meter square for your slab, and accordingly you will find the ordinates. Suppose I'm having it as 6 value and the UDL will be 0. I select, like you can get the previous selection directly from here as well. When we do that, all the beams are selected. I click on apply. So in this manner, the trapezoidal load can be applied for your beam as well. Then I click on close. I don't want to see this load. So again, I go to the assign and clear as display of assign. Now to define the response spectrum functions, like we go to the define option, but before that, I would say it is important to define the mass source. So we go to the mass source. As we know, the seismic weight has to be considered for any seismic analysis. So this is the mass source, and I can choose the specified load patterns. I can check off this. So for the dead load, I want 1. For the live load, suppose I give it as 0.25 to consider. And I will be using the different mass options for the lateral, vertical, and the lump lateral mass at story levels. So these options are checked on. I click on OK. Now I'll be defining the functions for the response spectrum. So I go to the function option in that response spectrum. And from the standard code, you can directly deal with the functions. So I go IS1893, I select that, and I click on add new function. So from the function name, like you can select, suppose I give it as response spectrum, you can choose what type of zone that you are having. Suppose I select it as zone 5 itself. So the seismic zone factor is 0.36, importance factor, I'm keeping it as 1. Soil type as 2, and response reduction factor as 5. So based upon that, these values are calibrated. So if you see the formula of AH, like that is nothing but Z by 2 into SA by G into I by R. So if you see here, I'm having Z as 0.36 for zone 5. And by if I'm having I in the numerator as 1, so it will not make any change, but it will change the value from the R and the 2 factor that we are using. So that is a factor of 10 coming in the denominator. Based upon that, this acceleration value is changed into 0.036 while dealing the Z with 0.36. So that is how you have these value. So it is important to note that this is in the terms of SA by G value, because when you apply it, you need to apply gravitational factor as well as the acceleration when you are applying it to the structure. So this is the function graph. I click on OK and I click OK. Now I will be defining the response spectrum load case. As of now, we have defined the function, and this is the EQX and the EQY that we want to edit now. So EQX, I make it as response spectrum. And from here, you can see the mass source as previous mass source 1. I click on add, and I have the acceleration, and it will be applied in the U1, that is the global X direction. And I'm choosing the function of RS that I just defined. And you can see the default scale factor that is coming here is 9.81. So that is how like you can choose. And then you will find the different combination of model that I mentioned, like in the response spectrum based upon the combination method, your results will also vary. So I have chosen CQC and the model load case. I do that and click on OK. Similarly for the MY, I choose this as response spectrum. And this will be applied in U2 direction. Select the function, scale factor as same, and we click on OK. So we have defined the response spectrum functions, gravity and the static loads. I click on OK. So we are almost done with the linear geometry of our structure and with the load cases to be defined. Now, before performing the analysis, like you can, I'll just quickly save my file. I have not saved it yet. So I'll go to the now when you go to the analyze option, you have the option to check model. So I select all these things, click on OK. So message will be shown like model has been checked, no warning messages were generated. So it means like the whatever modeling that we did was correct. There was no errors in that. There might be some mistakes while dealing with, I would say, inputs, but the program will check whether the connections and everything is made properly, the links and the diaphragms that we are providing are done correctly or not. So these are the warnings that the program calibrate, but you need to be ensured whatever values that you are giving as the input. So once this is done, like we go to the analyze option and we can choose a set load cases to run. So I have these cases as of now, and I'll just run them. So for the scale factor, I see like there are, okay, for the scale factor, like I see there is a confusion between 9.81 and 9810. So to give the clarification on that, you need to check the units here. So that is nothing but mm per second square and meter per second square. That is the 3 decimal spaces shift that you might see in case you are dealing with per second square, because I changed the units for my acceleration as meter per second square. So if you see the unit form, here you can see the time related acceleration. It is done as meter per second square. That is why I've chosen this value. In your case, it is, if it is per second square, then you can keep it as 9810. Okay. Now coming to the deformation, like the analysis is done, you can see that over here, we go to the display option and I can choose the deform shape. So for the different cases, we can check the deformation. Suppose for the dead load, we are seeing, I click on apply. It is shown for that itself. For the EQX, if I check, so you will see like how it has been excited for the X direction. Similarly for the Y in the Y direction. Then we can check the results, like the different forces. For the different load case, suppose for the dead load, I want to see the bending moment. So these are the values in case I want to check for a specific beam. So I'll just click on that option. So when you choose right click, that beam will be shown. So you will have all the bending moment, shear values at that location and how the deflection is done for your beam. And this can be then later on changed to the different loads that you want to see. You can check the tabular results from this approach, like go to the display and choose the bottommost option. And here I get to the structure output. I will be using the modal information. So I click on OK. I want to see the time period of the structure for the different modes that you can see now here. Like the model for the first mode, I'm having time period of 2.816. And for the later modes, it has been decreased. So this is the time period of my structure. And I can choose the participation, like I can see what are the participation factor for the different modes. So it is one of the critical thing to check on, like it is really important to design any building, like we ensure that the torsion modes are not the dominant one, because those are most dangerous thing. And in case the torsion is dominant, then we use the shear wall and everything in our structure. But here you see the mass participation ratio in UX is 0.74, while in UY it is 0.75. So I would say my mode is in the first mode is in the global X direction, while the second is the global Y. And when you see the summation here, so it is important to consider those many frequencies where the 90% mass participation is done for your different modes. If you see sum of Rx, Ry, Rz, so you will find that torsion mode is summation Rz is coming 0.75 for the third mode. That is how like you can check the modal results for your structure. Once your structure is, I'll quickly, yeah. So once your structure is like analyzed, you can create the different load combinations as well. By going to the load combination, I can use add default for the concrete frame design. Suppose I select that, click on OK. So as of now, you will see that these are the load combinations automatically created for 1.5 dead load and the live load, the corresponding factor. While for the earthquake, 1.2 factor. But as per 1893, we know like whenever we are considering earthquake in one direction, we need to consider 30% as well for the other direction. So you can make those changes to the load combinations. As of now, we are not focusing on that because we need to cover the pushover analysis as well. But that is the idea. Like you can make the, suppose for the EQX, when you're dealing EQI as a dominant, you will add EQI, and also you will have a response spectrum in Z direction that consider 2/3 of your AH value. If you see in the code, the spectral acceleration value for EQZ is also given, which has the factor of 2/3. So based upon that, you can add those response spectrum functions as well in the similar way. So once this is done, I forgot to define, I click on OK. So click on OK now. Now I can just go and design the concrete frame design as well. So if I go to that option, like here you can choose the design code that you want. If I keep it as IS456 and these values, like here the program asks for you, consider P delta done. So I'll choose it as yes. Then it will also ask for design of beam to column capacity ratio. So I keep it as yes. There are different factors. We click OK. And then I go to the design. We need to select the different design groups. So I will be selecting this all group that will consider all the frame elements. Then the load combinations. And then we can click on start design check. So you can see the design results in this manner. I go to the design option again, concrete frame design, and I can choose the different preferences that I want to see. So display design info, we select that thing. And I will be choosing the rebar percentage. So you will be able to see the rebar percentage that is coming for your column and for your beam. Then you can see the column beam capacity ratio as well. So generally we try to ensure that this column to beam capacity is 1.4, like the column is 1.4 times stronger than your beam. Like here you can see the different failures that are coming. And you can see like here, the design is not suitable, like we are having overstrength. So I need to increase the size of the column for these cases that I've defined. So what I will do, I will quickly go to the design. You can see this also, that's 36 concrete frame failed the design check. Do we want to select them? Yes. So you will be able to see them like here. Basically, these are the column sections. So in case I want to change them, I go to the define option again. We'll unlock the model. This will delete the results for us. And suppose I make it as I've increased the reinforcement and the size. I click on OK. Then I'll again run the analysis. So as of now, like for the earthquake forces, I believe like these columns are not passing, but I will move ahead for now. Like this will be an iteration process. We need to check how the structure is behaving, and accordingly we will update the member forces. But as of now, what we will do, we will move towards the next part. That is the capacity, like how we are getting the pushover analysis done and how to define the hinges. So for that, I'll unlock the model first. So this is unlocked. Now for the definition of pushover analysis, the first step is like we can define the load cases for the pushover. So I go to the load case type, and here I can add new case. Where I choose the name as pushover. Suppose I'm applying it for the y direction. I will be starting this from the gravity, and this will be nonlinear static type. I click on add. You have the acceleration and the different, like you can give to the different modes. Suppose I'm choosing it for the mode 1, and here I'm giving the scale factor for that. And I click on, like from here you can consider geometric nonlinearity option. So this is another thing that someone has asked, like how do we consider the p delta analysis? So you can, whenever you're choosing nonlinear static analysis, you have the option to choose the geometric nonlinearity as well for that load case. So I do that. And I have the option to choose the load application. So I will be using displacement control, where I can give the load to be monitored for the displacement of magnitude. And at the story height, I'm choosing node 6, like the joint 6, where this deformation is to be monitored. So basically, as we mentioned, like we get the capacity curve of the building, and we like transform it to the capacity spectrum. So that is why we need the maximum deformation, which will be on the top story. So I do that. Then I have the option to choose the results saved. So I will be saving it for the like for the different stages, multiple stages. So I select that thing, and I give the minimum number of saved states and the maximum. So I suppose I give the minimum as 30 and maximum as 50. Say positive displacement increments only. So I'll click check on this option and I click on OK. And click on OK. I see another message like where 520 members are feeling. So that is okay. Like the concept and the thing that we are here to discuss is about the application of the different design. Since the session is of like, I would say we are covering 1 hour for the demonstration. So it is not possible to design and give every loading in 1 hour. So if it is failing, that is okay. Like we just need to ensure that from the modeling perspective, all the definitions are done correctly and all the standard loads are applied. You can change the section properties, but in case 520 members are failing, so you need to check how the forces are also applied. There might be some problem with that because in my case, as I mentioned, like this story was failing. And I believe like that is because of the response spectrum function forces that has been applied. So we can check with that. Then again, like I've given the pushover for a direction and now I will be defining the hinges. So for that, we go to the define option. Under the section properties, you will find the frame wall nonlinear. I click on add new property. Yeah, we will share the recorded session, like recording of the video, since I know like at times people miss off the steps. So we will share the recording as well. So for the default for added hinges, like here you can choose the different hinges that are present. So if I talk about the hinges, so program and ETABS also provide the different automated hinges that can be provided. And also you can give the user defined hinges. So as of now, I will be defining the first hinge for my beam. So I give the name as beam. And for this, as I mentioned, like you will be using M3 curve. So I choose moment M3 here. And that will give me this value of the backbone curve. I will be updating this backbone curve as per the properties that I'm having. So yes, like this is the backbone curve we are having and the different moment versus rotation you can see from here. And these are the values. Then here we are having the immediate occupancy, life safety and collapse prevention. I can give these different values. I can choose this as not symmetric. So I can give the values for this. So as of now, I'm choosing iOS 0.01. This is 0.08. And I will be updating this backbone curve as well. So these backbone curves are obtained from the codes itself and also from the research paper. You can find the different backbones where the researchers has done and obtained this backbone curve after testing as well for the different properties. So I updated the backbone curve in this manner. And once this is done, like I can click on OK. And I can also choose the hysteresis type from here. As I mentioned, like in this case, I choose it as degrading, and I will be also modifying these parameters. So this energy factor I'm changing as 0.55. So one of my hinge for the beam has been defined. The next for the column, we define the fiber hinge. So I click on add new property. Then I choose the concrete again. Give the name as column. And I can choose here fiber PM2 M3. I can choose the hinge length and I will be choosing default from frame section. So what it does, if you choose user defined, you need to give the different inputs, like how your reinforcement is applied and what are the material corresponding to that coordinate, like what is the area that are to be considered and what is the material. So you can use different nonlinear material and apply it over here for your. So this is just a type of GSD, general section designer, where you link the coordinates with the nonlinearity of the material, or you can choose directly from the frame section. In that case, you need to give the nonlinear properties to the material that has been defined, and the different rebars can be considered directly from there. So I click on OK and I click OK. So I have defined the hinges. Now I need to define these hinges to my frame elements. We need to assign them. So again, we go to the frame assign option. And here you will find the hinges option. As of now, these are not like this is grayed out because we need to select the element from which it has to be applied. So I select properties, and under the frame properties, suppose I select all the beam like this. So once the beam has been selected, I go to the frame and I go to the hinges option. I will select the beam hinge that has defined. You can choose the auto hinges as well from here directly, which I mentioned, like from the code itself, you can choose the backbone curve from ASC 417. For M3, you can select directly from this location as well. As of now, we have defined the hinges there, and now we are assigning it here. I've defined the hinges, I click on OK. So now you can see like this has been applied to my frame elements. Similarly, I will be assigning the column hinges. For assigning the hinge length of element, like there is a formula that I cannot recall, but you must have learned in the courses, like there is a formula for the hinge length of the hinge calculation. Based upon that, you can calculate the hinge length. So this is like I've taken from the past study where I've calibrated that value, but it would be considered from those formula. Then I get the frame. I select column. And assign the hinges of column to that. Suppose for the column, I'm applying directly at the end. And I click on OK. So the hinges has been assigned. I can just clear display of assign. It is OK now. Now next, like we can go to analyze, set load cases to run. And then I can perform the pushover analysis. So it has not been defined, like I click on cancel. That is why like it is important to click on OK. So I define it for push Y, non-linear static, mass source, select that. Initial condition will be taken from the gravity load case where we have the dead loads and the live load factor. Then I select the mode. P delta. And we choose the multiple states to save the result so that we can obtain the pushover curve. Now you will find the pushover Y here, and I can just click on run option. Now. So it will take some time to perform the analysis. Meanwhile, I have the analyze model where I can just go So till that point, the analysis is done. Like this is the analyzed model for the similar geometry that we had. So to get the pushover curve, we go to the display option. And here you will have the static pushover curve option. So I defined for the pushover y, for which you can see here, like the curve that has been obtained, the base shear versus the monitor displacement. So the maximum base shear that you can see here is coming around 2212 kilonewton, which you can see here. And like this is the way the collapse is happening. So in this way, you get the pushover curve, and you can also get the capacity spectrum. Like as of now, we have done it for the pushover in y direction. It will be similar for the x direction as well. And another important thing that I want to highlight, as of now, I'm not sure we have kept that in mind, but when we apply the pushover, and suppose you are using the mode option, so the first mode, in case that is the y, then you will choose the pushover in y direction and give that as mode 1. But that is just the name. Like you can apply it in the push y and push x, it will be similar, but for the result interpretation part, it will be easier for you to understand. Like the mode will be defined for x is mode in first direction is in the x way. So we will be using push x and defining it for the mode x and choosing it as 1. So we check for the other options that we have. So as I mentioned about the FEMA ATC 40 that we have the results for. So you can
चाय पी ली है मैंने मैं चाय पी ली
So using this capacity spectrum and the demand spectrum, you can obtain the performance point as well. So you see like this is the red point that is shown, and for which my deformation is coming around 220. I would say it is 250. And we have the base shear as well corresponding to that. Like this is the spectral acceleration that I'm having. And the spectral displacement. So that is close to 260, which you can snap it from here. And this spectral acceleration is e to the minus power 3, e to the power minus 3. The value you can check from here. So that is the, I would say, significance. Like how do you get the performance point? Getting the capacity curve. Earlier that was the pushover curve. If you see the pushover curve, so this is in the way of base shear versus monitor displacement. But later on it was changed into capacity spectrum. I can check the deformed shape as well. So I keep it as 3D. For the different steps. Another thing that I want to talk about this pushover curve is also helps to give the ductility, like based upon the ultimate deformation you are having in the yielding deformation. The ratio of that gives us the ductility. So that can also be calibrated using the pushover curve. I want to see how the hinge formation is done. So I go to the push Y, and here I can set the different steps. Just a minute. You can see the hinge results as well in this manner by going under the display option. This is for the column. So it is like going in the linear range itself. For the beam, you can see the backbone curve, and we need to check like how it is covering that part just to calibrate the results. Like so, like suppose I'm seeing the results for this model. So this is the pushover curve. So I'm having the monitor displacement. So this is the yielding point. I can say that is close to 330 mm, and the collapse is close to 534. So if you check the ductility, it will be close to 1.8 to 1.9 that you are getting here. And similarly, if you have the ATC, so you can see like how you are getting the performance point at this location. And for the performance point, you can say your deformation is 386 mm, like it is close to, I would say, 400 mm. So like you can see like this is the seismic demand of your structure, because for the hazard curve, when you are intersecting it, the capacity curve, this is the deformation that you are getting. So in that way, you can have the performance point. Similarly, if I check the hinge results, so I go to the hinge, display, hinge results. So here you will find the proper hinge for the beams as well, and for the columns as well. So here you can see like we need to find the particular element which is forming, which is like following this hinge pattern that we have given. So you can see this cross option, because based upon the demand, the different, we have given the part to follow, but it is not necessary every beam will reach that point or will have that much demand. So that is how you have this thing. So in this way, we get these results for the hinges. And I was talking about the hinge formation. So for that, I will just quickly get the deform shape. Okay, there is some problem with the software, I believe, because with every model, it is not able to showcase the hinge formation, but you can check the hinge formation in this manner. Like you choose the load case and you have the different steps for which you have done the analysis. And in that manner, you can have the hinge results shown. Like based upon that, we get what level of occupancy has reached for your hinges. So now we will be taking up the questions. Like I move back to the presentation and
Mr. Mihir, if you want, I
yes.
can read out the questions.
I do have that window, although like.
Okay,
Maybe
but I
can-
have sorted out all the
Okay.
questions so that it will be easy for us to discuss. Yes.
Okay, that will be great then.
Okay. There is a question by Mr. Salman Mihir. He says, in which situations we should use pushover analysis and time history analysis respectively?
Okay. I would say like it depends upon the requirement of an engineer, like what type of structure we are dealing with and where that structure is located. Because at times, as I mentioned, like pushover analysis has to be calibrated with some other type of dynamic analysis where the, I would say, action of earthquake is considered, because pushover analysis gives us the capacity of the structure, but it doesn't give the requirement. Like we are using ATC, according to that we get that, but the more accurate will be the time history analysis that actually apply the ground motion on the structure. But it is important, as I mentioned, the ground motions that are to be considered. So the selection of that ground motion is also important parameter. We usually don't have that much data. That is, if you can add anything to that.
And there is a follow-up question. It says that you talked about the effective stiffness of RC frame members, right? Where you have quoted ASC 4113, where they have given some effective stiffness values for different structural elements. But if you see, there are several codes which suggest the effective stiffness values in addition to ASCE. So which values we need to consider, or is there any specific guideline which one needs to follow?
I would say, like, if we are performing these dynamic analysis and considering FEMA, so in that manner, we can consider ASC values that are done, because those codes are synced together. But when we are considering only response spectrum analysis for our for Indian structures, so there we are following IS 1893 for the response spectrum. There we can use the stiffness provided in that code.
Okay. So it is like wherever we are constructing a particular structure, and based on the location, if that particular code gives the guideline of the respective effective stiffness, then one needs to follow that. Or otherwise, any international guideline which is a generalized, which gives us a generalized parameters that one can go for.
Yes, true.
That's your recommendation. Okay.
Yes.
And Mr. Kiran is asking that what value of effective stiffness we should consider, especially for shear walls.
Okay, just let me go through the presentation. I believe there it might be added, like I've taken the codal value. So here you can see, like, these are for the walls. I need to check, like, for this must be for the shear walls.
I think the last row, it talks about the shear wall only, the cracked section.
Yes.
Which says 0.5 times of modulus of elasticity into the gross area of that particular section.
Yes, because like we generally don't consider the brickwork and the infills as the structural component. So this should be the shear wall.
Okay. Mr. Kaush is asking, can we use non-linear static analysis on the existing buildings to check its performance?
Yes.
Can we do that?
We do that, and like in the industry as well, that is the case. Like we perform that thing, and you need to ensure what are the strength of the material that you are incorporating there. Like you can have the sample from the site and just check what is the compressive strength value and everything, or you might have the past data. Accordingly, you can model that thing.
Right. Okay. And especially when you model these existing structures, the input parameters, I suppose, is very important, especially the material properties.
Yes.
If somehow, if you can gather all that information, either by using some NDT test or some core cutting test, and then those parameters can be given in order to analyze the performance of an existing structure.
Yes.
Mr. Dipanshu is asking, can we perform pushover analysis in STAD software? Is it possible?
I'm not sure about the STAD, like I'm more versed with the CSI software and with the MIDAS one, but I don't recall about the 7.
Fine. There is a query from Mr. Shivang which says that what is torsional constant in the frame element? It is not clear to him.
So I discussed it during
your voice,
presentation as well, like when we have the model through this. So likewise, we give the coefficient to the stiffness modifier to the M3 as of now, but for the torsional constant. So we can give that torsional constant as 0.1 when we don't consider that the slab is actually integrated with the beam, because at times we don't give the development length at the sites, and that is where like torsion, because the torsion in the beam is the bending in the slab in the different axes.
Right.
So that is how you can actually simulate how the ductile detailing is, or the detailing is done at the site, and you can release those effect of the forces.
Okay. Okay.
Mhm.
Mr. Ravi Chandran is asking how to incorporate the design eccentricity clause, which is given in IS 1893, to a real model.
Okay. I believe we have that option somewhere, like I'm not recalling it, but like we have the option to consider the eccentricity as well when we are performing these dynamic analysis. So maybe I'll check and I can get back on that thing. Like where is that
Okay.
option present? Yeah.
Okay. Okay. Mr. Millen is asking that how to determine this plastic hinge length. Is there any empirical formula available?
Mhm. Yeah, so as I mentioned, like there is an empirical formula, but I'm not recalling the name, but it is present. You might recall like yeah.
Because in your analysis you might have considered 0.1 meter
Yeah.
in the column hinges, right?
Yeah.
So he's curious how you have calculated that.
Yeah, actually I've taken this value from the past study, and during that I've used in that empirical formula for which the equation and the name, like I'm not able to remember for now, but that is present in the curriculum as well. Like when we, like in M.Tech thesis, when we did that, it was present in the curriculum. So I will find that in my notes maybe, and I can share like what
Sure.
empirical formula is used. Yeah.
Sure. The next question is how to obtain this. Let's say his question is related to the capacity curve. Especially, let's say if a capacity curve is showing some kind of a brittle nature, right? But in order to make it a ductile, how to do that? Whether we need to play with the reinforcement or whether we need to change some sizes in order to obtain a proper ductile curve.
I would say like it is majorly dependent on the backbone curve that we are giving for the beams and the columns, like for the beam specifically, because in this case as well, like I'm not able to showcase the hinges, but the hinges are formed in the beams. And if you see this backbone curve, just a minute, like. So you see, like initially we had the curve which was drastically falling from here. So that will give you the more brittle nature. But when we are adding this, I would say the ductile behavior, like how the not yielding is and post yielding the plasticity is occurring in my moment curvature. So that actually gets reflected in the pushover curve as well. So that thing is important to define the backbone curve when you want to have the ductile behavior.
Okay. And especially these parameters, hinge parameters, from where we get all this information, what are the values which needs to be considered? Is there any specific literature one need to follow?
Like they can use the FEMA and the ASC code. They refer those values as well. Like from the auto hinges option, you can find those inputs, and at least you can understand what are the parameters that are critical to define. Like there are some hysteresis coefficients as well when we are choosing the model as degrading. So the different coefficient corresponding to that are present. As of now, whatever that I've used are taken from the research paper that was published beforehand. So from that study, I've taken the values.
Okay. Okay.
Yeah.
And one of the participant is asking these levels, right? Immediate occupancy, the collapse prevention, the performance levels, which are mentioned in the different guidelines. Whether they need to be changed as per the requirement, does these values really vary as per the structure height in particular?
I would say it depends upon the requirement on the sites, like what the code specifies, and also what type of material we are choosing for that. Because based upon the material behavior that you are choosing, the behavior, because stress strain curve will be following that behavior. So you need to ensure when the linearity is
Mm.
moving towards the nonlinear range.
Right. And as you just mentioned that there is always a provision of auto-generated hinges or user-defined hinges. Which one do you think that will give the better results? And how to converge on the pushover steps?
I would say if there was a specific auto hinge that was the absolute correct hinge, then there won't be any other hinges being defined. The functionality and the usage varies from situation to situation. So I believe like it is dependent upon the engineer, like how he's doing his research background, like what type of property he is incorporating in his model, and accordingly the hinges will also be defined, because we have the hinges for moment, axial, and also for shear as well. So you need to take into account those things.
Okay.
Yeah.
And currently, for this particular model, have you used the response spectrum as per the Indian code or the ASC spectrum, Mr. Mihir?
As of now, I've defined it as per IS 1893. Like I've chosen for zone 5. Yes.
Okay. Okay. And there is a question which says that what will be the effect on the pushover curve if the columns are modeled as a lumped plasticity hinge? So the question is more related to a modeling strategy. Suppose if you change a modeling approach, if you choose a different kind of a model, maybe a fiber hinge model or a lumped plasticity model, do you think that there will be a significant impact on the shape and the properties on the pushover curve?
I would say it will depend upon the geometry of the bridge. Suppose I'm having a straight, like I'm having this kind of geometry where there is no irregularity. So I'm pretty sure like the hinges will be formed at the ends.
Right.
That is why like we have made it in that manner. But suppose there is some irregularity or some connections at intermediate locations as well. So we need to provide the hinges there as well then, where the mechanism can be formed.
Okay. So currently for the beams and the columns, we are providing at the ends, right?
Yes.
Right. Okay. And suppose if we are also modeling the infills, then we need to provide the hinges accordingly. There may be an axial hinges in such a case.
Yes.
And there is a question related to fragility curve. The person is saying how to develop fragility curves through a time history analysis.
Okay. I actually went back a bit about it, like just to talk about this process. Like we have the different time history ground motions. Like in this case, as I mentioned, I was having a far field record set of 20T ground motion. Now I applied it transversely to both the direction in the combination. So that makes it a total of 44 set of ground motion applied all together. Then we have the different scale factors, like you give the different scale factors to the ground motions, and accordingly you capture the interstory drift ratio. When you capture this interstory drift ratio at some certain point of scale factor, there is some drastic change in this drift ratio. There we see like the mechanism is formed. That is why even the slightest change in the input intensity, there is a drastic change in the output deformation that we are getting. So that is where we say that collapse is occurring at the structure. And for this ground motion, this will be my collapse intensity, which is this SA. So similarly, we find it for all the time history. Then we obtain the result in this manner. Like this is the sheet that I personally created. Person can make it as per their need, but this is how I did it. I have all the motions and the scale factor and the spectral acceleration corresponding to that. Then I have the logarithmic values as well to get the record to record variability, which is the standard deviation of these values. Then I have the SA values for different collapse. And based upon that, I check the median. So if you see, like this is the median of this value, that is 0.23G. So based upon that, when we calculate these values, we have the formula which I showed. I used the Hazo's methodology, where the logarithmic distribution of C6, which is this SA, like we get the intensity of SA at different values. This is the collapse that I just showed as 0.23, and this is the beta. So beta is like under root function of record to record variability and also the modeling deviation that I'm having. So that was chosen as 0.5, while this record to record variability was 0.32. Based upon that, I can just calculate these values, and that will nothing but it will be the probability of collapse for the different spectral acceleration, which are these. And then you can plot the curve in this manner. So that is the process of it.
Okay. Thank you. Thank you, Mr. Mihir. And there is a question from Mr. Karam Chandani. He's asking that since you said, right, at the time of design, approximately more than 500 members were failing. So he's asking that, is it possible to fix up the element size automatically by any software which failed in the analysis? Do we have such kind of any option?
I would say like that whenever the element is failing, we need to change the parameters, and in different software, you will have the different possibility, like how it can be changed. If I talk about ETABS, like you see, like I've given the different material section properties, I need to go back to the section properties and I need to update them. And if I talk about MIDAS, so in MIDAS, we can similarly just create any new section as well. And I can just select these elements and drag and drop. By using drag and drop, I can define the new section properties to any of the elements. So it varies based upon the software, but the general principle is like we need to update the section properties.
Right.
Yeah.
Okay. I think these all are the queries which I have found in the chat box. Now I open the floor to all the participants. If there is any specific query, you can directly ask to the speaker. You can unmute and you can ask the question, if there is any. I think Miss Yati has one question. Yati, if you are there, you can ask to the speaker directly. Any of the participants who want to ask any specific queries? I think there are no more questions.
Okay.
One question I have found in the chat box. The question says, how to assign a plastic hinge for a shear wall?
So if you go to the assign option, here you will find the options for frame and shell, and here you will find the hinges options as well, the wall hinge.
Okay. Okay. And this is not a question, just one comment. Mr. Millen is asking, right, how to determine the plastic hinge length. So my answer to that is, there is one literature, one research article by Mattock in the year 1967, and it is most commonly used in the research fraternity to calculate the length of a plastic hinge. And the equation is very simple. It says 0.5 times the effective depth of your cross section plus 0.05 times of section modulus. And section modulus also you can approximate to 0.5 times the length of the beam, right? So where this LB is the distance from the hinge to the point of contraflexion. So with that formula also, one can easily calculate the plastic hinge length. So I really want to thank you, Mr. Mihir, for sparing time for this hands-on training session, and to introduce the nonlinear seismic analysis to all the participants, and also highlighting the different types of modeling approaches and their applicability as well, and along with the comprehensive hands-on training session. So I really thank you for the for the kind of effort you took, and it's been almost more than 2.5 hours already.
Yeah.
Yes. So now I hand over the mic to Ipshita. Ipshita, over to you.
Thank you, sir. Thank you, sir, for giving your valuable insights on non-linearity and seismic analysis, pushover and time history. Thanks for explaining the modeling of RC building for non-linear static pushover analysis. So now I would like to pass on to Shubhkar for the vote of thanks.
Shubhakar, I think you're muted.
Okay. Am I audible right?
Yes. Go ahead.
Yes.
Hello, sir. Hello, everyone. I'm Shubhaka Visumba, pursuing M.Tech in Computer Structural Engineering at IIIT Hyderabad. It's my honor and privilege to propose a vote of thanks on behalf of IAStructE, IIIT Hyderabad Students Chapter for this occasion. First and foremost, I would like to thank our guest speaker, Mr. Mihir Jain. Despite his busy schedule, he has found time to grace today's webinar. Sir, I thank you for sharing your valuable knowledge on the topic, understanding nonlinear analysis of RC buildings, which is of great interest to structural engineers, research scholars, and industry people. Thanks for providing insights about material contact, geometrical.
Yeah, Shubhakar, please continue.
Yes, sir.
It got
Yes,
disconnected.
yes. And also about static, seismic, and response spectrum, pros and cons of Pushover analysis, time history analysis, and also when to perform static equivalent and dynamic analysis method, and what is building fragility curves and Hayes methodology, and also lumped plasticity approach and disturbed plasticity approach, and also incorporation of non-linearity in RC buildings. I would like to express our heartfelt gratitude to our faculty advisor, Dr. Praveen Kumar Venkatrao, for his valuable guidance and timely suggestions. And my sincere thanks to Mr. Srikanth, the IT team, Mrs. Babita, Mrs. Grace, for providing all logistic support, help, and assistance. I also thank all those who have directly or indirectly helped us to make this event successful. My special thanks to all the participants for their active participation and enormous cooperation. Last but not least, I also want to acknowledge the effort, support, and cooperation of my entire team in making this webinar successful. Finally, I want to end this program by extending my sincere gratitude to all of you for being with us and making this event a grand success. It was indeed a great pleasure. This concludes our webinar. Thank you all for attending. We hope you have learned and enjoyed this webinar.
Thank you, Shubhakar.
Thank you, everyone.
Thanks once again, Mr. Mihir. And
No problem.
next time, if we get the opportunity and if you can spare some time, then we can have a dedicated session on the time history analysis as well.
Yes,
Yes.
for sure. Okay.
Okay. Thank you.
Thank you, everyone.
Thank you so much. And I also thank to all the participants for their patience hearing. And I hope you all got benefited with this hands-on training session a lot. Thanks.
Hello.
Yes.
Sir, I'm Arundhati. I have a request, sir.
Yeah, Arundhati, please go ahead.
As far I'm concerned, it's been a long, I am working with this software.
Okay.
So as ETABS, I'm working on ETABS for the first time. So if you are getting the demonstration part of the lecture as a reference, it would be very helpful.
Yeah, sure, Arundhati. So I'll talk with the speaker first.
Okay.
And yes, and we would like to share and disseminate the knowledge as much as we can. So
Okay.
if the speaker agrees, then since we have already recorded the video, and
Okay.
if there is no conflict of interest, and then definitely we will share it with all the participants,
Okay.
so that the knowledge will be largely disseminated to each and every one of you.
Okay, it was very informative session, sir. Thank you so much.
Thank you. Thanks a
Okay.
lot. Okay, Mr. Mihir.
Thank you, everyone. Thank you, sir.
Okay. Bye.